Hello there, and welcome to another video in the How the ByteFrost Works series. Last time, we looked at the fetch operation, the process by which the ByteFrost loads the next instruction in our program into the instruction registers. In this video, we'll complete the simple CPU operation model by looking at how the ByteFrost executes instructions. Let's begin by examining what instructions are. From a programmer's perspective, instructions are the most fundamental way to tell the computer what you want to do. Here is a list of the current implemented instructions in the ByteFrost. As you can see, there aren't that many. At the moment, we only have 20 different instructions. We have seen in episode 1 that instructions are represented in code as 16-bit strings that contain information such as the opcode, which is the ID of an instruction, source and destination registers, immediates, and other relevant information. We can think of these strings as function calls. We tell the CPU what instruction we want to execute and provide the relevant arguments. However, these say nothing about how the instruction itself should be executed. There are, in essence, three parts that influence how an instruction will be executed. First are the relevant hardware modules in the CPU. If we want to add two numbers, for instance, we need the ALU, the arithmetic logic unit, to contain an adder circuit to perform the addition. Second is the instruction string, which contains all the necessary arguments for the instruction to run. This is our function call. And thirdly is the microcode of the instruction, which is a sequence of microinstructions. In this video, we will focus on the third aspect, but we'll discuss the first two as well. Let's examine a very common instruction, the add instruction. Technically, this instruction isn't a part of our instruction set, but it is an instance of the ALU instruction. Let's examine what we need to do to implement this instruction. In assembly, a common way to write this instruction would be add rd rs1 rs2, which means add the values of rs1 and rs2, the two source registers, and store the result in rd, the destination register. We can see that two hardware modules are relevant to this instruction, the register file, which houses the source and destination registers, and the ALU, which will perform the addition. The particulars of which registers are the source registers and destination registers and which ALU function to use, in this case addition, are sent directly from the instruction registers to the register file and ALU, respectively. In the ByteFrost instruction set, bits 12 to 15 of the 16-bit instruction string are reserved for any parameter registers. Hence, we can essentially send these bits directly to the register file's address input to specify which registers are being used. The same principle occurs when sending the intended function to the ALU. How, then, do we tell the ByteFrost to execute the add instruction? Let's first go over, in high level, the necessary steps for the add instruction to be executed. First, we need to send the value of the first source register, rs1, to the ALU. The ALU has two dedicated input registers, registers A and B, so we'll send rs1's value to register A. Next, we need to send the value of the second source register, rs2, to the ALU's other input register, register B. Now that the ALU has both input values, it will produce the sum of those values. We should note, however, that there is no trigger to tell the ALU to compute the addition of the input values. The ALU is combinatorial, so it always computes the sum of the input values. However, we only care about the result when the two inputs are specified correctly, as they are after we've loaded registers A and B with the values of rs1 and rs2, respectively. Hence, although the ALU was computing the sum of the inputs already, only now will it output the correct result. Now, all we need to do is send that result to rd, the destination register. Notice that nothing in these steps specifies how to actually perform the addition. They only specify how data needs to be moved from one place to another. As the two modules involved in this instruction are the register file and the ALU, we could simply extend wires to connect the register file's data input and output to the ALU's data inputs and output. However, there are other modules in the ByteFrost, and if we took this approach, then we'd need to create a specific connection between two modules whenever we have an instruction that requires it. This would require a lot of wires and, more importantly, complexity in controlling which of these connections are activated at any given time. Instead, the ByteFrost uses a data bus, a long strip of 8 wires suitable for transferring 8-bit quantities to which every module connects its data inputs and outputs. only one module can write to the bus at a time, and when it does, all of the modules connected to the bus receive the data it sends. However, we can control which modules read from the bus, so if we specify that a module should not read from the bus, it will ignore the input value. The result of this is that every clock cycle, the effective connection between modules changes. For instance, in one clock cycle, the ALU and register file are connected. In another, the ALU is connected to the RAM. In this way, we have a framework for easily connecting any two modules by specifying which module writes to the bus and which module reads from the bus during a particular clock cycle. The way in which we specify which modules read and write every clock is by microinstructions, which essentially send read and write enable signals to the modules we want to connect. So, how do we convert from the high-level steps we've outlined to microinstructions? Here we can see a list of the 8 fundamental control signals we had when we implemented the ALU instruction. Each control signal can either be 1 or 0, indicating that it is on or off during a particular clock cycle. Hence, each microinstruction is defined by which control signals are on or off. That means we can write a microinstruction as a byte, where each bit represents the state of one of these control signals. Let's see this idea in action by writing the microcode for the ALU instruction. First, we need to load the value of register RS1 into the ALU's input register A. To do this, we need to tell the register file to write the value of RS1 to the bus, and the ALU to read the value from the bus and store it in register A. Hence, we need to turn on the control signals of register file output enable and ALU load register A, which we can do by setting the respective bits 4 and 1, to 1 in the first microinstruction. Hence, the first microinstruction is 12 in hexadecimal. Next, we need to load the value of register RS2 into the ALU's input register B. This is very similar to what we did in the first microinstruction. First, we need to tell the register file to write the value of RS2 to the bus. We already saw that we need to turn on the register file output enabled control signal to do this, but as we want the register file to specifically output the value of RS2, we also need to turn on the register file output select control signal. This control signal is necessary since we have 2 possible source registers in our instruction string that we need to distinguish between. Now that the register file is writing RS2's value to the bus, we need the ALU to read that value and store it in register B. Hence, we need to turn on the ALU load register B control signal. Writing out the microinstruction, we need to set bits 0, 3, and 4 to 1. This means that our second microinstruction is 19 in hexadecimal. Now that the ALU has the 2 correct inputs, it will compute the sum we want. All we need to do is send the sum to the register file. To tell the ALU to write the result to the bus, we need to turn on the ALU output enable control signal, and to tell the register file to read the value from the bus, we need to turn on the register file input enable control signal. Now it appears that we are done. We have specified all of the necessary behavior for our instruction to work. However, recall from the previous episode that each instruction causes the instruction after it to be fetched by sending a PC advanced signal to the fetch state machine. As this is the last microinstruction of the ALU instruction, we need to send a PC advanced signal in order for the next instruction in our program to be fetched in the next clock cycle. To do this, we need to turn on the PC advanced control signal. Hence, altogether, we've set bits 2, 5, and 7 to 1 in the third microinstruction, making it A4 in hexadecimal. What does this look like in the ByteFrost? Here, we see the ByteFrost running an add instruction. These LEDs show the microinstruction that is currently executed. Each bit is labeled with the control signal it represents. As this is the first microinstruction, we can see the LEDs that are on, labeled ALU load register A and register file output enable, matching the microcode that we just wrote to send the value of RS1 to the ALU's input register A. Now in the second microinstruction, we can see that the control signals for ALU load register B, register file output select, and register file output enable are on to send the value of RS2 to the ALU's input register B. In the third and last microinstruction, we see that we have the ALU output enable and register file input enable signals turned on to send the result of the ALU to the destination register RD, but also the PC advanced signal is on in order to fetch the next instruction in our program. And there you have it. We've gone over the simple CPU operation model and showed how instructions are fetched and executed by the ByteFrost. This completes the 3-episode trilogy that covers the fundamentals of how the ByteFrost works, so in future videos we'll have free rein to look more closely at particular modules of the ByteFrost, and also talk more about the ByteFrost capabilities by implementing algorithms. The exact slides that were referenced in this video are indicated in the video description, and if you have any questions, please put a comment down below or create an issue on GitHub. Thank you very much for watching. If you liked this video, please subscribe so that you don't miss future videos.